Right. So in the last class, if you've seen how the current direction changes, I'll still repeat very slightly as it goes through the change in flux, and you know plot this gradient, right? The things I'm marking over here. That gradient, when you plot in a current versus time graph or axis, what you get? You get something similar to this, right? You get something similar to this. So it can be EMF, it can be current. So that is current. Okay. Why is the current graph and EMF graph same? The reason it is same is V is equals to IR. There is a direct proportionality between voltage and current. So EMF induced and the current in the coil is exactly proportional. Granted, you understand that. What I was talking about is how it makes sense that the direction of current changes. So when it is in this position, right, BA considered in this position, in this orientation, and it cuts through magnetic field lines as it rotates, there is a current induced, let's say, I forgot what direction it was, but let's assume it's in this direction. Now, later, when it has turned 180 degrees and is in this specific position, so if I show it to you in this position, that is, right? Um, BA. So basically, there will be A and B over here. Got it? Is that A and B? No, B and A. So it will be B and A in this position. That is, it has rotated 180 degrees. So you know what happens over here? The thing that happens is the direction of current from in this direction goes to backwards. So the direction of current has flipped over here. You know why? Use your right hand grip rule. Initially, when the flux is happening in this direction, that is, change in flux is happening in this direction, it is rotating clockwise, let's say. There's a flux change in this direction, that is, the magnetic field change into the plane changes. That is, there is an increase of magnetic field lines into the plane that is cut through BA conductor. That is segment BA. It cuts through a bunch of magnetic field lines that is into the plane. So to compensate for that, it produces magnetic field line that is BA. It will induce a current in BA that produces a magnetic field line that is out of the page. And if you use your right hand grip rule right now, so it will show that initially it is from B to A. So our initial assumption was wrong. So initially it is B to A. And then when you have this, where this is B and this is A, over here, you know what happens? So when it is cutting through magnetic field lines, which is into the plane, it will now, due to Lenz's law, produce magnetic field lines that is out of the plane. And over here, if you use your right hand grip rule, you will see if this is, sorry, if that is B and this is A, your right hand grip rule will indicate your thumb in this direction because it is creating an out of the plane magnetic field line. It is inducing a current in the wire, that is, the flux change is inducing a current in the coil such that that induced current creates its own magnetic field out of the plane to compensate for the increase in magnetic field lines into the plane, that is of north and south. So in this entire interesting process, a flip has happened in direction of current, right? That is why you see a flip in axis, my friend. That is why you see a flip in axis. Initially, it is in the positive direction. Doesn't matter which direction you consider positive. The notion over here is initially it is in one direction, and in the next cycle, it is in the opposite direction. That is what we want to establish. And that is the core idea of having alternating current. Two reasons we say it's alternating current. One, the magnitude varies with respect to time, and also the direction of current varies every half cycle. That is the fundamental behind alternating current. If we understand that, I will move on to today's new topic. That is, it starts over here. Okay. So if you have any question till now of the concept of alternating current, how it makes sense, why it makes sense, and what it really is, you can ask me. I'll give you the floor for asking me. If not, I'll move on to explain the next part. Okay. Okay. Good. Great. So we start off with features of alternating current. When you have an alternating current, what do you know? It is a cycle of current. We can agree. Whenever you have any such sort of sinusoidal graph, we call this what? Sinusoidal graphs. It's a sine graph, it's a cosine graph. These are sinusoidal graphs. And the thing with these is they have a certain frequency because it's oscillating. It's an oscillation. Okay. So they have a certain frequency. What does that mean? That is, every cycle is completed within a certain time period. That is to say, every 1 second, there will be a certain number of cycles. If I repeat myself, if every 0.1 second there is one cycle, in every 1 second there will be 10 cycles. Simple maths. Fair? So basically, my point is an alternating current, and you will hear this, see this in your appliances and everywhere around you, that they have something called a frequency. It can be 50 hertz, it can be 60 hertz. These are the common ones that you will see or know of or have seen on certain devices specifications. So, how can I mathematically explain this, show this to you? Omega is what? 2 pi by t. Okay? Omega is what? 2 pi by t. That is rate of change of theta, if you have forgotten. So, I can also take 1 by t and say this is frequency, and that is right. And I say omega is ultimately 2 pi f. I can also make frequency the subject, which is my entire point, which is what I want to do, and I get omega by 2 pi. Okay, so this gives me ultimately um, the number of cycle that is oscillation per second. Oops, per second. Make sense? Okay. So now let's put this idea into action. What is the dynamo, by the way? This entire thing is called dynamo. So if this is spinning, right, and it let's say it's spinning at a rate of 50 complete cycles every second. So it has a frequency of 50 hertz. Okay. So every oscillation is being completed in around 1 by 50, right? So let's put that into perspective. So what would the frequency be? There is what theta is being covered. Oh, it's not 50 cycles. Sorry, my bad. It is 50 pi radians covered, not 50 cycles. So what 50 pi rad per second is? It's the omega. So rate of change of the theta. So that is the omega itself, not the number of cycle per second. So ultimately, what do you do to get the frequency? You get 50 pi divided by 2 pi, which ultimately gives you 25 hertz. So give me a moment, please. Give me a moment. Yeah. So ultimately, what is this giving us? The number of cycle per second. So in this question or in this case scenario, they've given you the amount of change of theta, amount of change of radians per second. So you divide by 2 pi, that is one entire oscillation, and this gives you ultimately the number of oscillation, which is the frequency of this entire situation in this alternating current situation. So in essence, if they tell you that this entire thing rotates 25 times per second, you immediately know that the alternating current frequency is 25 hertz. Okay, so basically how many times it oscillates per second. Fair. So if you understand that, let's give me a moment again. My bad. Yeah. So ultimately, now we can model this. Granted, we know it's an oscillation. I can model this entire thing into a sinusoidal graph. There is the oscillation itself. How do we do that? Ultimately, we will say that current can be expressed as an amplitude times any sort of um, trigonometric function over here. But usually, normal case scenario, we're going to be using sine. That is to say, it oscillates from 0 to 0. And this is the oscillation, what it looks like. This is how we consider it to be. And this entire graph, if it's a sine, if it's a cosine, depends entirely on how the dynamo is set up. How the dynamo is set up. So it depends entirely on where the flux change we start considering. Okay, so the standard is we consider sine. So let's say if the dynamo was at 90 degrees, that is, it was not in this position, not in this position. We start the dynamo in this position. Then we don't say it's not. We don't consider it with respect to a sine because it doesn't make sense, right? Because over here, rate of change of flux will be the maximum. So then it becomes a cosine. So in that case, you know what the formula for current would be? It would simply be I naught cos omega t. Okay. But this, I don't think, will be in your exam. This they won't ever really ask this or pose this as a question. I've never seen. They may give you a very conceptual question and ask you express current in terms of a trigonometric function to express the AC current. So in that case, if they, for example, they can show you that that dynamo starts in this position, right? That is vertically. And in this case, what do you say? You will say that it's I naught cos omega t. I don't think they'll do that. I've never seen it, but standard is I naught sine omega t. And you will ask me what is omega t, and I will ask you revise oscillation chapter. That is to say, omega times t essentially gives you theta. So as time increases, theta covered keeps increasing. Initially, it is 2 pi, then it keeps increasing 4 pi, 6 pi, 7, whatever the number is, 8 pi, so on and so forth. Okay, so omega t gives you the theta. Okay, so no confusion over here, hopefully. Good, great. So if I had to define it for you guys, what AC is, it is simply a current which periodically varies from a positive to a negative value. That is a positive to a negative current with respect to time. That is what alternating current is. Now comes to new notion, new chapters. What are the new chapters? So right now we're going to talk about the root mean square of current or voltage. So this concept has never this was covered slightly in your ideal gas chapter. Okay, so there was the notion of having root mean square because we have positive and negative values. To omit that, we square all values, take the magnitude, and then take a root of it, which allows us to have ultimately only positive values. Okay, that we can work with, and it is a great assumption to make because our answers are very accurate when we do that. Good. So I that is what it is in ideal gas when you learned it, the root mean square notion. It is very similar to that. It is pretty much exactly same to that. We're just going to apply it in our case in a different context. So what will the root mean square value give? It will give a value of voltage or current that is analogous to having a DC current such that both produces the same power. What on earth did I just say? Okay, I'll explain it. So if you have an alternating current, right, and you have this expression, I varies from I naught, sorry, I wrote cos. Let's see, you have alternating current and you have I is equals to I naught sine omega of t. This is the expression you have. So this current, my friend, your final current or your varying current varies as a function of sine. So there is no one current that will determine the power in the circuit. So in this case, when you have alternating current, Essentially, you can say the power varies. Okay, the power varies essentially, but it is not exactly true. Power can be expressed as I square R. Okay, I just said that power can, in in logic, power can vary based on having the current varying, but it is not true. It is not exactly true. Why do I say that? It's not true. That let's say you have alternating current, right? And you have a continuous supply of alternating current. This will have a certain heating effect, which we express by I square R, or since this is often considered heat dissipation, or the amount of power due to having, let's say you studied this in IGCSE, that there was a significant heat dissipation due to having high voltage in transmission lines. I believe somewhere you have seen this formula, P is equals to I squared R. So my concept with you guys is, as the current varies with respect to time, right? It is constantly doing some amount of work. What is power, my friend? Work done per unit time. Okay? Work done per unit time. Now, this entire process of having alternating current varying with respect to time, overall, having a symmetric graph such as this, which is symmetric, let's say, about the x-axis in one sense, and is also symmetric about, if we take, let's say, just this portion, this one period, it is symmetric about this point as well. Okay. So my point to you guys is, as the alternating current works, as the current varies, it dissipates a certain amount of energy. Okay. Or it dissipates a certain amount of power. And it has, even though the current is varying, it will have a certain constant heating effect, or a constant power dissipation. And you can figure that out. You can figure that out. How? You don't take the max current for that calculation. You don't also take the minimum current. You find the root mean square value and work with that. So the idea is the current varies with respect to time, but overall I can take a certain average to say that the power dissipation can be calculated with respect to this average current. So I'll repeat in a bit of a summary, right, what I just said. As the current varies with respect to time, I can take a certain average of this current, and you'll see how we do that, and consider that value of current to be causing the power dissipation. And that is the same current that if I have a DC circuit, that is one constant current value, it will dissipate the same amount of power. So if this is, let's say, a DC current graph, and this is an alternating current graph, right? So point is, this alternating current and this DC current should produce the same power. That is where we want to go to. That is, how do I find from an alternating current situation a constant current that produces the same heating effect, the same power dissipation? How do we do that? How do we find that constant current? Okay. So in essence, what is the average current as the alternating current works, as the current varies with respect to time? What is that average current? That is what we want to find out, and that is where we take help of root mean square value. So let me give you the situation. What happens as current varies through I naught times sine omega t? There's a resistor over here for the power to dissipate, or for the voltage to be used essentially. So this is how you show alternating current supply. So current is traveling in both direction, right? And in both cases, right, when you have a DC supply and when you have an alternating current, in both cases, they're supposed to dissipate the same amount of energy or power, whichever you want to say. Okay. Now, in case of an alternating current, it is just that the direction is varying and the amount of current with respect to time is changing. So what will we do? We will find a certain amount of or a certain average current. Okay. Such that we say if a DC current supply has the same amount of current, it will dissipate the same amount of heat. And what do we do to do that? There are a few steps. There are three main steps. I will find the I naught square value. You see this I naught, max current in an alternating current situation. Max current in an alternating current situation. I will find the I naught square value. Then you know what I will do? I will find the mean square value. Okay. And I'll show how we do this. And then you know what I will do? I'll take a root of that mean square value. And I get the mean current value. So what did we say? We wanted to find out the average current. And this is ultimately you get the average current. So in this entire process, there's a bit of math involved, and I'll show it to you. No worries. Let's take a situation. Okay, let's take a situation to understand this. Let's say we have an alternating current with 3 amps. That is to say, that's the max current. Okay. So when they say that you have AC supply of 3 amps, that's like the I naught value. Okay. So I is equals to 3 times sine omega t, valid, where amplitude is 3. Good. And when I show this graph, give me a moment. There are a few things over here. Okay. There are a bunch of graphs. When I have the orange graph, if you just notice very carefully, it varies between positive and negative value. And this is your alternating current value. Okay, the AC current supply. And you have I naught as 3. Good, fair. Now, what is the first step? Finding the I naught square. Okay, what is the I naught square? What is I naught? 3. What is the I naught square? 3 squared. And that is 9. So I know the I naught square value. But that is not the entire point. I am showing this graph to explain a bit more to you guys. What is that? Look, how do we get the I naught square? For one thing, we squared the amplitude. That's very simple. I understand that. But what is essentially happening? You have I is equals to I naught sine of omega t, right? And then what I'm doing is I'm squaring all of these variables over here. Okay. And what do you get? This I square value is essentially the sine square curve. Okay. So I have taken the entire current thing and I've squared it. The entire AC supply of current, I've squared it. And I get a sine square curve, which you are you know of from pure maths, how sine square looks. So this entire negative portion gets into the positive section, positive axis. Okay, good. Now, the reason I'm showing the purple one, give me a moment. So the reason I'm showing this purple graph is to make sense of the mean square value. And the thing is, you get to this point, right? Sorry, you get to this point, I naught square, that is 9. How do you get to this? Pretty confusing. The reason I say confusing is how do you just find out the average value? I know that the I naught square value, the maximum current squared is 9. But what is the average squared value? The I square value varies like this. Are you getting me? The I square value varies like this in the positive axis, but it varies. But one thing is also true. I told you guys towards the beginning that this entire graph is symmetric. Is what? Is symmetric. Why do I say this? The reason I say this is if you take an average of area under the graph, okay? If you take an average of the area under the graph, what we can find is the I0 square value, the average I0 square value is exactly half of I0 square value. So it is exactly half of 9. So 4.5. You know why this happens? I have explained in very details over here with almost too much details. If you take a snapshot of this, I will not do this because you will find this very boring. But essentially, what I do is I take all of this area, I sum it up, and divide it. I divide that entire thing, all of that value, by the time elapsed. Now, what I get is average with respect to time, with respect to 1 second. I have 4.5 amps of current running through the circuit on average. So, what do? I integrate it under the graph with respect to time, right? That is the area under the sine square curve, divided it by the time elapsed. Take any period, by the way. You can take up till this point. You will get the same answer. I can guarantee you will get the same answer. If you integrate, let's say, the sine square value, which I did over here. So if you integrate the I square, this 3 square uh, times sine t square, and you integrate this for, let's say, 1/2 cycle, right? For half the cycle. You know what you will get? 4.5. So what does this show you? This is the proof, by the way. I just made it up. So that is the proof that if you have the I0 square value, the maximum square value of current. So if 3 is your AC current, what is the I0 square value? 9. Okay. And if you take the half of that, that is 4.5. That is the mean square current running through your circuit. Mean square current. So what is the mean current now? Take a root of it. Take a root of it. So root over 4.5. And that is going to be around 2.12. And that, my friend, is the mean current running through the entire circuit. Okay? Average current running through the circuit. And if you input that into the power equation, that is the power dissipated by an alternating current worth 3 amps, which varies with respect to time. And that is also the power dissipated by a DC circuit, which has a current of, what was the value? 2.12, I guess. 2.12 amp. So an AC circuit with a rating 3 amp will produce the same power as a DC circuit with 2.12 amp. Why? Because even though this is said 3 amp in the AC circuit, the net or the average current running through the circuit is actually 2.12, which I just showed to you guys in some essence. Okay. So I just did this in Desmos. You can try and play around. I plotted a bunch of graphs. I took a little bit of integration and then found the average value to prove that if you take the half of max current in an AC current supply, that gives you the mean square value. Okay, that is half of max current square value. Okay, I0 square value. That is the max value I'm talking about, and half of that will be the mean square value. And take a root of that. Finally, you get what? The mean current. Okay, 2.12. What is the shortcut to all of this? The shortcut to all of this is the root mean square value can be found out by I0 by root 2. This is a formula if you want to memorize, and you will have to memorize. I'm pretty sure none of you guys will do all of that. But it is good to understand the concept of what is happening, how we get the average current in the circuit. So now look, what is this? It's simple derivation. Okay. We say that the power in AC should be equal to the power in DC. And the power in AC is the mean square current times resistance. Why? Power is I square R. Okay? And we're simply taking the mean square value. Why? Why are we taking the mean square value? Only because the current varies in AC. It is not constant. It's not 3 amp always. It varies. Okay. So the mean square value is going to be I naught square divided by 2, which we just showed. Whatever the I naught square value is, 9 divided by 2, 4.5 is the mean I naught square value. Okay. So that is expressed by this. Okay. Resistance and resistance gets cancelled out. So this is your mean I naught square value. And over here, what is this? This is basically the root mean square value that I'm finding out. That is, this is exactly what I want to make the subject. That is, in to have the same power in DC circuit, I want the root mean square value of the average current in an AC circuit squared times R. Okay, this is also following the formula I squared R. Okay, so I make I RMS the subject. I take a root over on either side. Ultimately, what I have is I naught by root 2. Okay, so this is the short proof of how we get root mean square current. So essentially, you take the, if you have, let's say, AC current with current supply 4 amp. Okay, you say the root mean square in that AC circuit is 4 divided by root 2, whatever the value this gives you. This is your average current in the alternating current supply. Or you can say, if this current, whatever this value is, if this current is provided in a direct current circuit, it will dissipate the same amount of heat or power. Got it? Any question? I did talk about some very confusing stuff till now. But any question till now about any of this? Is it clear? Yep. Okay. Now the same thing applies to voltage. If the current is varying, voltage also varies, as I showed to you guys, in the same proportion. So what is VRMS, or voltage root mean square value? You just say, well, I want to find the VRMS. So what do I include in my equation? It should be current times R, which is the normal equation. Does resistance vary? Not at all. Resistance is same regardless of its alternating current or direct current. But for current, I can have a different value in an AC supply and in a DC supply. And to find the average current in an AC circuit, which value do we take? The root mean square value, right? So to find the average voltage in the same AC circuit, which value of current should we take? Obviously, the average current. And well, we are using the word average and root mean square value interchangeably in this case. Okay, so the root mean square value is, in essence, the average current through the circuit. Okay, it is not entirely true, I would say, in some theory, because the average can be found out some other way as well, and it differs very slightly. But it works over here because of the square proportionality between power and current, which you don't need to really understand or respect right now. It's simply that we have to square the current, which is why we go through the entire process of finding I naught square, then finding the average I naught square, then taking a root of that I naught square average, and finding the root mean square current to satisfy this equation. Because over here, we are squaring the current. And when we do the root mean square process, we get the accurate value apparently. So that is why the entire root mean square process is done. There's another way to find average where you just, you know, find the area under the curve and simply divide by 2 and then take a root of that value. Anyways, that is besides the point. Right now what you have is the root mean square current expression, and the same applies to voltage root mean square expression. You just take in that current root mean square and input it into the voltage equation. There is no extra bit for the voltage. Okay, it's simple. You can also do like the substitution of the IRMS expression, that is this entire thing. You can substitute this into the equation, sure, which we have done in the second step. And this gives us a more clean equation only with respect to voltage. So if they have given you the max voltage in the, you know, circuit, then you can simply divide that by root 2 to get the root mean square voltage or average voltage in the circuit. Okay, great. And as mentioned, that this thing that we did, we squared the value, of whatever the maximum current is and divided it by 2 to find the average squared current. This only works when you have sinusoidal waves because there's symmetry over there. Okay, I haven't said it, there's symmetry, but yeah, there's symmetry in the way trigonometric functions work, which is why this thing works. Because a way to think about it is the white space and the area under the curve is equal. That is one way to think about it. Okay, so that is why it's exactly half half. So when you take a half of this area under the curve, you truly get the half mean square value, which is why it works. Anyways, it is also a bit besides the point, but in case you have any confusion or knacking towards it. Now, what is again in your syllabus is a few more expressions. Okay, they can ask you in an AC circuit that what is the maximum power in the circuit. And in that case, what you really do is take the maximum voltage value, take the maximum current value. This gives you the maximum power. You could also do maximum current squared times resistance. Or you could also take the maximum voltage squared divided by resistance. Okay? And the mean power, okay, would be taking the average of the voltage, that is root mean square voltage, or average of the current. And you can substitute each expression over here, and ultimately you will get is half times V naught times I naught. Okay, because essentially root 2 times root 2 is half. Okay, I mean 1 by root 2 times 1 by root 2 is half, which is why ultimately you have half times V naught times I naught, and this can be explained as what? Maximum power. So the mean power is half of maximum power. Okay, so I will re-establish something right now. Towards the beginning of this section, I said what? Power kind of varies, that is true, but we don't really say that. We say on average, there's a constant dissipation of power. And the reason I said that towards the beginning of this entire section is because you can technically say there's a maximum power in this circuit at a certain point when voltage is maximum and current is maximum. But you can, what we usually would say is what is the mean power dissipated by this circuit? Which is why I say it is a constant. Technically, it is a constant because there's a certain mean value that is dissipated, mean power value or mean energy that is dissipated by the circuit. On the other hand, if you are instantaneously analyzing every position of a graph, sure, you can say at this position the power is different, at this other position the power is different. That is not wrong. I don't say it is wrong. It is simply that there are two ways to look at it. You can analyze every position and say, okay, power is different at all of these positions, or you can look at the entire AC circuit supply with respect to time over an average amount of time and say there's a certain average power dissipated by this entire circuit, which we say the mean power. Okay, so this is the entire story. This is the entire story we have. Okay, fair. Now, this, well, average current. Yeah, this is what I was talking about, that we don't necessarily need to do all that square and the entire process that we did to find the average current. You can also find average current in a different way, which will yield you a bit of a different answer as compared to the answer we found. Okay, and well, I won't show this to you because it is not relevant for us. It is not needed to understand. This is extra information that why we consider the root mean square path to find the average current. There is this way of finding average as well that yields us a bit of a different answer if you see. So you can take a look at it if you want to take a screenshot and just out of interest want to read it. I just wrote it up and made it up. So you won't really find it in a book. Anyways, it's just to build concept. And the reason we follow the path we followed above is because we respect this formula. We want to respect that formula. And when we take the root mean square value, our expressions come very neat. We get some very neat equations. Anyways, so that is the process of finding root mean square, current and voltage, and ultimately finding the average power dissipation and the maximum power in a circuit. We found a lot of interesting equations, so you should 100% take note of the equations itself and understand where it's coming from. Good. Now, rectification. Again, do any of you guys have any question, any confusion till now? Anywhere? Everything's good? Okay. So now, with wave rectification, what is this entire thing? Well, wave rectification is simply not wanting two different cycles of current. Basically, if I want a direct supply out of an alternating current, what do I do? That is to say, I only want current in a single direction. I don't care that the amount of current varies. It is simply that I don't want the current direction in the circuit to change. That is what I don't want. Okay? The magnitude of current may change. It's okay. So that is where wave rectification comes into play. How so? Let's see. The rectification is basically a process of converting alternating current into direct current and voltage. Okay. So since your direct current, sorry, alternating current varies between a positive and a negative value, that means that the direction of current is changing. And if you want it in one direction, what we can do is either we can do two things. One, two. We can omit the current in the negative axis. That is, we won't allow current in the opposite direction, block it off. And the process is using a diode. And the other process is we use full wave rectification, where whatever current is coming from the opposite direction, I redirect that current into the same direction. And I will show this. And this is one of the most interesting things I find in this chapter because it's very smart the way we use alternating current to ultimately get direct current. They basically so that our power output is more technically we can transfer more energy, you could say, right? So we don't want to lose this current essentially. That is why I find the process of full wave rectification very interesting. So essentially what's happening in half wave rectification, we just don't allow opposite direction current. In full wave rectification, we take the opposite current and direct it in the same direction as the main one. So what does the technical process look like? How does it really work? We want to see that. Okay, let's see. Let's first think of half-wave rectification, right? And in half-wave rectification, it's actually very simple. You have, let's say, some amount of current, alternating current supply. You have a diode, okay, and you have some sort of an appliance which is using up the voltage. Okay, so in this entire process, let's say the current is flowing. Have I drawn it? No. Let's say current is flowing in this direction. Okay, the diode would allow the current to flow in that direction. Okay, so for the entire half cycle, there is current in the circuit. Now, what happens when the terminals change to this side is positive and the other side is negative? Well, it starts off, but then it's blocked at this position. It can't go. So the circuit is incomplete. So for the next entire cycle, there is vacancy. There's no current. There's what? No current. So this is what it looks like without a diode, and this is what it looks like with a diode. Okay. So there are some technical names you can think of or note down. One is where you have forward bias, so you allow current to flow backward, and you have reverse bias, where correct this, which doesn't allow current to flow forward. Okay, so there are two ways to think of it. There's a forward bias, there's a reverse bias. So it doesn't really allow, in case it doesn't allow uh, the current to flow. Okay, so it's just the opposite of each other. I mean, this is honestly oversimplified in some sense. If you do end up studying electronics, engineering, stuff like that, you will learn these in way more depth than it is covered right now. But anyways, so in half-wave rectification, you have one diode which allows electricity to pass in only one direction. Therefore, you have, in essence, less power being dissipated through the entire process. That's a given. Because for half the cycle, for the entire half cycle forever, there is literally no current. Okay, so the power is reduced. That is the notion over here. Okay, and oh, the other thing is, a lot of people have this confusion: is this even direct current? Is this even direct current? It's a wave, even if half a wave, it is a wave. And my answer to you is obviously it's a direct current. It's the definition of direct current is it allows current in one direction, not how much it provides or if it varies or not. That is not a part of direct current's definition or alternating current's definition. So for direct current, it's simply that it provides current in one direction. And for alternating current, it is simply that it allows current to flow in both direction. You are used to seeing a constant supply of current, which makes sense because often even people just automatically say that alternating currents sort of feature is the current amount varies and direction varies, which can be misleading because people would think that, okay, in case of DC current, it should be a constant current supply. I may have probably towards the beginning of this class said, okay, for alternating current, the feature must be that the current amount has to vary and direction has to vary. But in essence, really, for alternating current to work, it is simply the direction notion that is the current flowing in both direction, then it's alternating current. If not, then no. If it allows current in one direction, it's direct current. Okay, that's a core fundamental that you guys should have clear. Okay, smoothing and everything I'll show at the very end. Uh, I will be explaining all of it to you guys. No problem there. And now with full wave rectification, this is a bit more technical. I have to step by step show everything. So let's say you have this entire complex setup. Okay, and in these two processes, it's the same setup, by the way. Don't get confused. In these two processes, I'm going to show how for both half cycles, one where there's a positive terminal here, negative here, There's a negative here and positive terminal here. So in both cycles, how there is a constant current through the appliance or constant direction of current in the appliance, that is the resistor. I'll prove that to you guys, no worries. Okay, great. Now, let's start off with the one on the left. How do we prove that? Let's say I have current flowing from the positive end over here. Basically, I have a setup of diode to allow current in a certain direction. Okay, so I allow current in this direction. That is the conventional current route, and it can't flow over here. Nope, it will flow straight through here because the diode allows, and it will flow through this because it over here it's again blocked off. So it flows through that, goes through the resistor, comes back here. And by the way, this is not a junction, this is an overlay of the wire. So one wire is below, one wire is above, they're not connected. So it goes through here, and then what do you think it would do? What do you think it should do? It could, it could do one thing. It could go here, and then here, 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 and it just goes on forever. Do you get what I'm saying? So it doesn't really do that. Okay? So it doesn't do that. What essentially happens is it will pass through this point, not the upper one. Why? Because it never reaches a negative terminal. And the electrons are smart like that. I mean, not that they're smart or they have brains, it's simply that they don't find the negative terminal, which is why they don't end up flowing in that wire. So it is just that over here, when it goes, the diode allows. Diode will allow, but it won't go there. Why? Because it's not reaching the negative terminal. So where will it go? It will go here, down. And then, right, this is a junction, by the way. This is indeed a junction. So it goes and comes back to the negative terminal, and the entire circuit is complete. Let me redraw it. Goes through here, down, left, up, down, left, up. And you guys need to be very used to this. These are questions which will come in your way. You have to draw the direction of diodes. It is less physics and more puzzle in my eyes. Okay? It is less physics and more puzzle, the way I look at it. So get used to this. Drawing diodes and setups where full wave rectification is possible. Okay, so how does it work in the opposite direction? I'll show that to you again. Let's say this is now the positive and this is where the conventional current is going to be. Again, this is not a junction, so it doesn't have an option to go here or here. It's just an overlay of the wire. Great. Now, will it go here? Obviously not. Will it go here? Obviously yes. Can it go here? Not at all. It has a diode, so no path there. Now it goes right, comes down, goes to resistor, power dissipated, comes down again, goes left, goes up. Now it has two things to do. It can come down again and do this entire motion forever for the rest of its life, or it can find the negative terminal if it goes up and reaches this negative terminal, which is exactly what it does. So that is how the circuit is complete. Again, I'll redraw it. Goes here, 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 up, up, left. Sorry, oops. And reaches the negative terminal. This is how the circuit is complete. Okay, this is how the circuit is complete. Okay, clear? So in both directions, what did you see? Whenever current is flowing, either in this direction or in this, in both cases, the current in the resistor is flowing downward. Always. So the direction of current in the resistor is constant. In the wires, anything can happen. But in the appliance, what is happening? In one direction. Okay, fair. So, okay, this is the voltage in, right? This is the voltage in, that is positive, negative, positive, negative. And when rectified, it is all positive. And it's very, again, very interesting to me how this works or how clever the setup is. So the advantage is a larger power output. If you have all of the, you know, wave in the, I mean, of the current in one direction. Obviously, if you take the average of this now, it is a larger average of power. Okay? It is a larger average of power. Very simple. Make sense? Good. Now, what do? We are almost towards the end of the entire alternating current chapter. We do have smoothing, but that is pretty much it. Okay. Now I'm going to talk about smoothing. The entire notion of smoothing is simply decreasing the variation in current that you have when you have full rectified or half rectified current. Granted, the supply was AC. So the entire process of smoothing is basically to keep the current somewhat constant. Okay. So now, if I have to give you a proper definition, what would it be? It is simply the reduction in variation of the output of voltage or current. Good way of putting it. Now, let's say you have this half wave rectification with at your hand. How do you work with this? What I end of the day want is I don't want this current to go up and down and then zero up and down and zero up and down and zero. I don't want this. What do I want? I want it to be relatively constant. I want it to be relatively constant. So I want the variation to be as small as possible. It can vary very slightly, and as less as possible, I would like it for whatever reason. Right? For whatever reason. That is not of substance to us. But point is, our objective is reduce the variation in current. Now, how do we do this? We get back to our chapter of capacitors, and it's very useful to us over here. How? I show it to you. You have voltage in. Okay, you have voltage in, and let's say that is AC supply, and it allows half wave rectification because there's a diode. So now, from the current coming in this direction, can split into two places. Agreed? And when it splits, it charges the capacitor and it allows power output at the lamp. Okay, so the voltage across these 2 points are same. Voltage across these 2 points are same. So the voltage out at the current, sorry, at the lamp is the same, and the voltage applied across the capacitor is also same. So now, for the entire half cycle that you have, right? For this entire half cycle, what happened? The capacitor got charged up. Fair. The capacitor got charged up to the voltage of supplied. Okay. How long did it take to charge up? This long. Okay. So for this entire time period, till half this cycle, okay, I mean half that wave, the capacitor got charged up. Let's say this is V0. And now look, the supply voltage or the voltage in is decreasing, but the capacitor is charged at the same V0 level. So now the capacitor will discharge, okay, along with the voltage supply decreasing. So basically, the capacitor discharges. So you have voltage from the capacitor, and the voltage in the circuit decreases. Okay. So now let's see in graph what really happens. Okay, I'll show it to you. So for one thing, what I wanted to establish is for the entire half cycle when there is positive flow of voltage, the entire capacitor gets charged. And then for the next half, what happens when there is no voltage supply? And by the way, why is there no voltage supply? Because let's say conventional current in this route it just cannot reach the negative terminal, can it? Diode stops it, right? So if you have half the cycle due to this, next half cycle is a blank. Why? Again, diode stops the current. Okay, makes sense? Now, during this empty period that you have, what happens? As mentioned before, the capacitor discharges. The capacitor basically a positive terminal here, and now the lamp is using voltage of the capacitor. Same voltage. It is just that it's going to dissipate with respect to time, or the voltage of the capacitor will decrease. And again, you know what will happen? The voltage, let's say, of the capacitor decreases and will again get charged up due to due to the next cycle of current flowing through this direction. So it gets charged, discharged, charged, discharged through and through as the circuit works. Okay, so that is where the use case of capacitor comes in. It discharges when there is no current. It is not even that it is only possible in half-wave rectification. It starts discharging from the entire, from the top over here. It starts discharging from over there. So when the voltage starts dropping, the capacitor starts discharging. Okay, and I'll show that again. No worries. Okay, that is what I talked about. Fair. Hmm. So this is what I was saying, that that discharge that I just drew for you guys. Hmm, it's a bit of a wave. And what kind of wave is this? E to the power. Let's see. Okay. Do you guys remember this? This is the time constant formula. Basically, how long it takes, or the variation of current, voltage, or charge in the capacitor with respect to time. If you guys remember this formula, let's say Q is equals to Q naught e to the power minus t r by RC. These formulas are V is equals to V naught e plus t RC. You guys should remember these formulas, okay? So based on those formula, I'm saying, well, the current is varying like this in the capacitor when the voltage starts to drop from the supply. So again, we draw this, okay? I draw it for you for the entire first one period of time. Let's say 1 unit time. I have till half t, that is this point, the capacitor got charged up. And from this point onward, the capacitor starts discharging. Agreed? The capacitor starts discharging. Again, it gets charged from this point actually, not from this point. It starts charging up and then it starts discharging. Again, this point it starts charging up, again discharging. And by the way, you will look at this graph and be like, why is this so weirdly shaped? Why is this not more like this or like this? It should be steeper, right? A few people do ask this, and it's a good question, that why is this drop not steeper? The answer is this graph, this orange bit that you see, is the sum of voltage due to the capacitor discharging and also the voltage due to supply. Look, till half T, it says not that the supply voltage is zero. The supply voltage over here, V in, is not zero. It is simply decreasing. And the capacitor compensates for that decrease, not exactly compensate, basically provides the balance voltage, not entire balance voltage because the capacitor also discharges, but basically provides more voltage than there is from the voltage in. So the capacitor gets entirely charged up and it starts discharging. Okay, and this orange bit that you see is the sum of the voltage due to the voltage in plus capacitor discharging, which is why it is not a steep drop as you see for typical discharge graphs for capacitors in current, charge, or voltage. So that is why it is a bit of a flat or less steep, I can say. So essentially, when you omit all of these things, that is, all of these half waves, this is the current that you have, the net current. So it is the sum of voltage in half wave rectification plus the capacitor discharging. And now you can also broaden this discharge. That is, you can have it somewhat like this, a higher or more constant. A current can be less varied. And how do you do that? How do you do that? Time constant. You increase it. You increase the time it takes for the capacitor to discharge. You can do that. It's possible. Okay. Mm, okay. I did cover that. Okay. How to control smooth? This is what I'm talking about. What is time constant? R times capacitance. So how do you increase this time constant? You can simply increase the resistance of the appliance. Sometimes you may not want to do that. You can simply increase the capacitance at the very least, so it stores more. Okay. So at the end of the day, if you have increased the capacitance, it will discharge that energy at a slower rate with respect to time. So this red that you see is with a higher capacitor. Higher capacitance. Or you can also increase the resistance. Both works. Both pretty much works. Okay, great. So next, how would it look like? Any confusion till this point for half-wave rectification? No, all good. Perfect. So, okay. Now for how it looks like in case of full wave, full rectification. So this is the setup, which again, I'm saying this, you need to understand the setup as well. Questions to come around this. So you have this part you have seen above. This is the addition. This yellow bit is the addition. So you take a capacitors and put it parallel to your resistor. Understood? Okay. So the voltage across this is the same as the voltage across capacitor. Okay. Good. So same thing happens over here. Till this point, capacitor charges, starts discharging, charges, starts discharging, charges, starts discharging, so on and so forth. Make sense? Makes sense to me. So in this entire process, again, the capacitor is charging and discharging. The moment the EMF falls or the voltage in, okay, the capacitor starts discharging. Good. This is what I've talked about a bit before right now. Okay, perfect. Okay, this is the type of graph that you will usually get. This is why I'm saying it's more of a puzzle than anything else. And in these cases, all you have to do is a bit of tracing. Okay, you start tracing out what the possible routes are, and then figure it out. That what kind of diet should I put in. So let's say this is the positive side for one cycle. So this part was not given. Okay, you have to fill it up. And you want a DC output over here. Doesn't matter if this is the positive terminal or this is the positive terminal. Doesn't The question doesn't care about that. Any side could be a positive terminal. It's just that that side should be the positive or negative terminal for all the cycles. Good. Now let's see how it works. Current comes in, conventional current comes in, and it can't go in here. That is a given by the question. So I want a diet that allows current through this. So it's easy for me to say that here the diet should be forward facing, not backward. Okay, there should be a forward bias over here. Okay, so I allow current through this. Now, technically speaking, you still don't know if you want what kind of a diet you want. I'm going to assume that over here there is going to be a backward bias. So I have such diet that doesn't allow me to go in. So essentially, this one I'm guaranteed. This one I'm still iffy, which technically as a student, if I was solving this question, I would have gotten this diet, and this one I would still not have known for sure. Okay, so now I'm till here, and over here I want to pass through and reach a positive terminal. So I've established that this is the positive terminal, and I say this is positive, and this should stay positive for the next cycle as well. Good. So let's say now alternating current supply changes next cycle, and current starts through here up, and there's a backward bias over here. It doesn't allow forward current. So great, that's good. I have current through here. And now the point is, now I'm guaranteed that it should be a forward bias with respect to this point over here. Now I am certain that this is the die that I should have a forward bias with respect to this point. So now it goes, comes back, and positive. Does it make sense? So this terminal, this is the DC output. This positive terminal never changed. It is always positive. Make sense to all of you guys? Good. Any question? No?
No question.
Okay, perfect. So now we are done with the entire alternating current chapter. Very good. It's fairly easy in comparison. And what else do you have
Sir,
actually? Yes.
is there any sort of question, example question?
Yeah, the one I just showed, that was in your exam paper. You're talking about these questions, right?
Is there any more like usual, quite difficult stuff?
More difficult? Yes, I could show you. Wait. This is a bit different, mm, but you can think of this. You can try this. 97024 2MJ21, essentially. I can give a run over this question. I haven't showed steps over here. But anyways, so reference to heating, explain what is meant by root mean square value. It is simply the current needed in a direct current circuit that produces the same heating effect as alternating current. That is simply the answer. Over there, use figure 10.1 to determine the peak value, root mean square value of the current, and the current I1. Okay, so it's simple. You just read the boxes over here, and once you do that, you'll find the peak value, and it is also called I naught. Okay, root mean square value. How do you find root mean square value? Tell me. Anyone? We just learned the formula right now.
The peak value over the square root of 2.
Perfect. I naught divided by root 2. Okay, so this is the current RMS value of the current. Perfect. That is great. Now determine the peak value and the RMS value of the I2. See, this is why I remember now why I have done this thing. Now I remember that because of that question. This is why I did this elaborate explanation over here. So, for this, I will for one thing ask you to do this. And the peak over here is simple. Peak is right over here. Okay, 2. Peak is 2. And this is, by the way, a question that a lot of people got wrong. This exact question. If you check the examiner's report. Okay. So now, what is the root mean square value? What is the root mean square value? Let's do the entire process, the entire shenanigan that I did over here. Everything that I did over here. Let's do the entire breakdown of process. I will first do what? I will do a square of this entire thing. So the square of this entire thing will look like somewhat like this. Okay. So this is 2, and this is 4. And this was -2, and it will become +2. Sorry, +4. Positive. So it's a call. This is the I square value, I naught square value, or I square value. So this is the constant value. So that is the mean square value. Okay. The mean square value is 4. And what is the root mean square value? Root over 4. And that is going to be 2. Answer is 2. Yes, answer is 2. Are you confused about what I just did right now? Did whatever I did make sense? Sorry?
So that again.
Which part? The entire process that I did over here for finding root mean square value.
Yeah.
Okay. So what I am doing right now is not following the formula. Okay. What I am doing right now is the elaborate process I followed to explain the concept of root mean square to you guys. What was the concept, my friend? The concept was simple. Three things. You find the I naught value. Okay. That is I naught, sorry, I naught square value, whatever the max value is, square that. Okay. And then find the mean square value. Okay. Once you find the mean square value of current, then find the average current. How do you find the average current? You take area under the curve divided by how far of the area it is, that is on the x-axis. That is how you find the average. Okay.
Okay.
Okay. So those are the few steps. And the last step is, by the way, I was talking about this step. And the last step is take a root over whatever the average is. That gives you the ultimate current average. Let me show you in this case what I did. First step, I will break it down into steps only for you. So right now I have this. What do I have? Positive 2, negative 2, positive 2, negative 2, positive 2, so on and so forth. This is what, by the way? Is this AC or DC? Tell me. This tell me.
AC.
AC, perfect. It doesn't matter if it looks straight. It is not straight. Okay, it is going back and forth. Okay, so this is AC. Doesn't matter if it is rectilinear. Now, this is alternating. That's perfect. So, what was the first step? I find the square values. I naught square. Okay. First step is find the I naught square value. What is the maximum current?
2.
2. And that is the only current. That is what is fascinating about this question. That there is a variation in direction only and not the magnitude of the value. This is where they put the twist. Okay, you're used to this concept. Sinusoidal, symmetric about 1 point. This is new to you. So they are, it's not exactly new, it's very conceptual, but they are giving you a constant value of current. Forward 2, backward 2, forward 2, backward 2. Now, what is the max current? By default, 2. Okay. So what is the I naught square value? 4. So if I take a square of this entire thing, it becomes 4, 4, 4. So it's a constant. It becomes a constant value. What is the I naught square value? 4. Okay. So what is the average I naught square value? Mean I naught square value. What do you think? Tell me.
2/4. 2.
Sorry. So I'm saying I naught square value is 4.
Yeah, root
I'm,
over 4.
no, I'm not asking about the mean current. I'm asking about the mean square current.
Oh, it's 4.
It's exactly. It is 4. So right now the max current square is always 4. So there is no concept of average. It is always 4. So the average itself is 4. If you take an average of 2 plus 2 plus 2 plus 2 and divide by 4, what do you get? You get 2. Okay. So that is the point over here, that your max current is not varying itself. So your average I naught square is simply 4. And then what was the next step? Take a. So we are at this step. We are at this step. We found the I naught square value. Now, what do you do to find the mean I or mean current? Take a root of it, which you were just saying.
Sir, could I take a screenshot of that part, please?
Yes. So ultimately, your I naught is 2. Just a disclaimer again, I made this up. So, I mean, it's just an example situation to explain the entire concept. Which part, by the way? The graph part, this part.
Yeah, this part.
Okay, perfect.
Sir, could you zoom in a bit?
Which the graph? This one?
The 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 writings
Right.
under the graph.
The writing. Okay.
And so the one above the graph,
The one up. Yeah, this one.
above the graph, yeah, this one.
Yeah.
All right.
Yeah. Okay. Perfect. So now, which was the question? Where is that question? Yeah, this. So ultimately, our answer was correct. It was indeed two. Okay, and the reason I added star is because this was a bit confusing for a lot of people because they straight up went for this formula, which let's try that. What happens in that case? What is the max current? It is 4. 4 divided by root 2. Will you get the right answer? Tell me. If I use this formula, are you getting the right answer for the root mean square value for this scenario?
Yes.
How? I mean, I'm talking about the DC, well, not DC, sorry, it's the rectilinear shape AC supply. 4 divided by root 2 is what?
4 divided root 2 is, wow, yeah.
Exactly. So that this is the point. This is where, and this is the reason why people got this wrong. Okay. So most people would be plugging the max value that they saw to into this equation. S- My bad.
Oh, so I think we
Yeah.
can
So
only
they would.
use that
Yeah.
equation when it's a sine function, right?
Exactly my point. Exactly my point. You can only do that with symmetric graphs. So sinusoidal, the beauty of sinusoidal graphs are they're symmetric about their these points, and these are the only cases it works. This assumption only works in these cases. Got it?
Yeah.
Perfect. That is exactly what I wanted to explain. Rest, these are decently easy. You will be able to do these. It's just using the formulas. This is what I wanted to show. Okay, you can just skim over these. 97024 to MJ21. AC, I don't think has too many difficult questions. Where you will see difficult questions is I did share a video once. You will see a bunch of list a hierarchy of topics where difficult questions come. I'll ask you guys to follow these. Like let's say E field graph, very important. Magnetic field can have difficult questions if your concepts are not clear. If your concepts are really clear in magnetic field, you shouldn't struggle as much. And even for magnetic field, graph, as in, yeah, graphs come more, but I've seen electric field come more frequently. And then there's next 4 chapters that you guys have left. So yeah, next chapters that you have quantum, then astro, nuclear, and medical physics. These are a cluster of 4 chapters where interchangeably often difficult question may come, but it is very like easy to just learn the topics, learn the content, and it just ditto the questions that you're supposed to get. Very little creativity is shown in these chapters in terms of the quality of questions given to you.
Yeah,
My
it's
observation.
very, for example, most chapters, even if you understand the content, the questions are tricky, but here it's pretty straightforward.
It's
Most.
pretty straightforward for the content you've learned. That is what I'm saying. Exactly. So then E field oscillation, I will say, I have seen, and the entire thermal chapter, you will see some brilliant questions. Like I have seen a lot of teachers struggle with these questions, and I've shown that to you as well in when explaining. That's why I showed more questions in that like in those lectures. Those people tend to struggle because it's very conceptual. E-field graphs, oscillation, circular motion. If you understand the core concept, it will come attached often with separate um, topics. Then gravitational field is a good chapter. It again conceptual. It can be difficult. Okay, these are the topics which I would say has an essence of difficulty attached to those. And then the last four I will say is pretty straightforward. They can interchangeably make one question which is difficult that they are supposed to do. And the years I will ask you guys to practice years. Definitely do 5 years whenever you have your exam, whatever it is. Do 5 years for a fact, if possible by you. And if not, I'm looking for the chapters actually. Wait. Uh, Motion and several gravitational thermals, oscillation, electric field, capacitance, uh, capacitance and AC. Capacitance and AC. Okay. This I consider capacitance and AC. I consider almost one chapter. Like, I don't really see much of a difference in between these. These come attached often, and this is like somewhere in between these and these. By my observation, it's very subjective, but after I guess 15 years of paper, this is the core idea I've seen. But yeah, you do 5 years, and the papers you should do in complete and not just skim through the papers is you should try 21, 22, 23 questions in these years. 20, honestly, you must do these 21 and 22 and do the complete paper. Do the complete paper. And the reason I'm saying this, and this also applies for other subjects you do, mechanics or pure maths or chemistry. You know why these 2 years are very difficult? These were lockdown years, COVID years. And they made the papers and no one sat for it, and they made some abhorrent papers during this period. So the entire 7 plus 7, I guess you'll have 14 papers to complete. You 100% should do these. Good for building concept. Okay, that will be my general advice. And obviously, as many papers as you can do, always good. Fair. I will have to end the class at that for today because my AC is done. Hopefully, we'll be done with the rest of the topics in time. Any question that you guys have, do ask me right now.
No,
Okay, perfect. Uh, all good then. See you guys tomorrow, Saturday, same time. Okay, hopefully we'll complete the next chapter. What is the next chapter?
all right, thank you, sir.
Quantum. Yeah. Bye bye, guys.